Hey guys, we are discussing for this recording session chapter 18, the functionality of the urinary system. Um, Let me kickstart an annotation here. Okay, we're gonna go over reintroducing, refreshing our memory about the structural um, and functional unit for urine production, namely nephrons. So although I expect you to know the concept, these microscopic structures from anatomy, but I think it's worthwhile to briefly revisit them in the context of, with the objective of introducing later in the chapter, um, the physiological or the functionality of this amazing organ system. When we think about the urinary system, it's usually a second thought, but this organ system is actually our disposal, waste management center. So they are responsible to basically cleansing, clearing all the cellular waste, meaning the waste that are basically generated by our body cells. And not only that, amazingly also, this organ system is involved in maintaining our blood pressure uh, on a long-term basis. So 24/7, day in and day out, our urinary system, our kidneys are involved tightly regulating our blood pressure. So that's another aspect of this organ system that is not being appreciated by us. So we take our kidneys for granted for that. So I expect this is an amazing recording session to go over this important organ system. So with that said, we're going to go over, like I said, introducing again, reintroducing nephrons. When we talk about nephrons, what are they? How do they look like, and things like that. We're going to also highlighting transport mechanisms that we covered already, but this is in the context, this is the application of what we've learned so far. So that's why, most of my former students truly enjoy this chapter because they get to know now, okay, this is why I learned this. This is why passive transport mechanisms are important. This is why secondary active transport mechanisms are important because now I can put, a name to a face kind of thing, if you will. So they get to know exactly under which application is being, applied by the body using these concepts that they learn, passively at the beginning of the semester. And now they get to connect the dots. Okay, so with that said, let's go over nephrons. So nephrons are microscopic structures that you cannot see, with your naked eye. We are born with 1 million nephrons per kidney. And interestingly, we are born with, when we were conceived, the body generates multiple kidneys, but we ended up keeping only 2. And within each kidney, when we are born, there are approximately 1 million nephrons per kidney. And then they remain relatively stable until we hit the 4th decade in our lives. So starting around age 40, this is where everything goes downhill. So every decade after that, every 10 years after that, we lose 10% of these nephrons. And since these microscopic structures are differentiated structures, they are highly specialized structures. If they're gone forever. We cannot, unfortunately, regenerate nephrons in our kidneys. So when you are younger, like most of you are right now in your 20s, and if you don't take care of them, it adds up. You know, these assault on our kidneys, you know, they accumulate over time. So by the time we get to age 40, you know, instead of having, you know, starting at 100% and losing 10% after that, you might start up with 80% or 70%, God forbid. And it's really simple to keep them healthy. Just drink water. And this is why, you know, this is important. And we get to talk about that more in the second part of the renal physiology, because there will be 2 chapters dedicated for this. So today's recording is the first part, and the next recording will be completing the part with the second part. So just simply drinking water basically protects your kidney on the long run. And we'll come back to that. Now, in a nephron, we have 2 types of nephron. We have the cortical nephron, which is around 85% of all nephrons. They are responsible to produce dilute urine. The other category of nephrons are called juxtamedullary nephron. They are responsible to concentrate urine, and they are around 15% of the total population of nephrons. The cortical nephrons have a short loop of Henle, whereas the juxtamedullary nephron, they have significantly longer loop of Henle. And not only that, the capillary bed that is basically surrounding the loop of Henle's here, they are also different depending on the type of nephron that we're talking about. For the cortical nephron, the capillary bed is called peritubular capillary. Peritubular, P-E-R-I, the word tubular capillary. Whereas the capillary bed that is interacting with the longer loop of Henle in the juxtamedullary nephrons, they're called vasa recta, V-A-S-A, 2 words. The second word, recta, R-E-C-T-A. So the vasa recta interacts with the longer loop of Henle in the juxtamedullary nephrons, the 15% population nephron where they are concentrating urine when you are being dehydrated, meaning fluid intake is being compromised. And when you are properly hydrated, the cortical nephrons are doing their job, producing dilute urine with their shorter loop of Henle, which interact with another capillary that we call peritubular capillary. Within each nephron, it interacts with a beautifully designed, beautifully made capillary bed. And this capillary bed is unique, both structurally and functionally. And that capillary bed, we call it the glomerulus. So 1 glomerulus, 2 or more glomeruli. And this is why when we say glomerulus, it's unique. When you have a normal standard capillary bed, I'm trying to reproduce it here as a cartoon. Change color. So blood goes in and comes out. Okay, goes through here. Goes through here. Now what we have on this side, this is an arteriole. What we have on this side is a venule. And what you have here is your capillary bed. CB, okay, capillary bed. For simplicity, I have only showing 3 capillaries, right? In reality, there are dozens or more of capillaries because capillaries, they don't exist as a single capillary. They're too fragile. So the blood pressure that comes in, and if you have only one capillary, continuous with one arterial and one venule, that capillary will be burst. It will be, the wall would be bursted and basically, it will not be able to do its function. So due to the thin wall of the capillary bed, the reason why they have thin wall is because for, gas exchange and nutrients exchange. So we learn from anatomy, if you need to exchange a gas or a chemical, the best boundary, the best membrane is a thin membrane. And so all capillaries have thin membranes. And because of that, they are also very fragile, right? So they cannot sustain a lot of pressure. So if any fluctuation of blood pressure needs to protect them, otherwise you're gonna basically burst them. So because of that, capillary beds exist as multiple capillaries. Together we call it capillary bed. Now, this is a standard capillary bed, okay? The glomerulus is not like this. So a standard, you have an arteriole upstream and a vein downstream. In the case of a capillary glomerulus, I'm going to erase the venule here. And instead of a vein type, in the glomerulus, you also have an arteriole here. And you don't see that anywhere else, but only in a glomerulus. So in other words, you're having, on either end of the capillary bed, you have 2 artery-typed blood vessel. And by doing this, they can control the pressure inside that capillary bed. So we basically, the functionality of this, you can have a much more higher level of control of blood flow going through each glomerulus by having this design. Okay, so we have arteriole on this side flanking the capillary bed as a normal capillary bed. But what is amazing is on this side, you also, instead of have a venule, you also have an arteriole. So since we have 2 artery type blood vessels, we need to differentiate which one is which. So the one that basically brings blood to be filtered into the glomerulus, we call that afferent or so AFF, afferent arteriole, meaning A stands for arriving, so it helps you to remember. The A here, arriving. The one that exits the capillary bed, this is called efferent or efferent arteriole with an E. E for exit, so you remember, right? So it's leaving the capillary bed. So this E here is exit, so leaving the capillary bed, whereas that A is for arriving. So going into the capillary bed. Right? So that's the glomerulus. So that's why you see here the 2 names, afferent and efferent arterioles. Okay. And everything is slow. I miss my whiteboard. Okay. Oops. Take this out. And in addition to the capillary bed, the nephron is actually a series of renal tubes, renal tubules. So you have the renal tubule includes the Bowman's capsule, this head here, okay, excluding the glomerulus, okay? So the Bowman's capsule, because the glomerulus is not part of that renal tubule. So Bowman's capsule, proximal convoluted tubule, PCT. So this is a proximal convoluted tubule right here, downstream to the Bowman's capsule. You have the loop of Henle, the hairpin loop, this one here. And then it ends with the distal convoluted tubule, this part here, okay? So that's a nephron. So the renal tubule consists of 4 parts. This is a series of tubes. So Bowman's capsule, proximal convoluted tubule, loop of Henle, distal convoluted tubule. If you want to include the glomerulus, so when you talk about the glomerulus, with the Bowman's capsule together, they are called the renal corpuscle. This word here. So the renal corpuscle consists, this is a composite structure, meaning it consists of multiple parts. So the renal corpuscle includes the glomerulus, which is the capillary bed, and the Bowman's capsule, which belongs to the nephron. And inside that renal tubule, remember these are tubes, right? So inside that renal tubule, there's a fluid, and that fluid, we call it the renal filtrate. Renal, R-E-N-A-L, filtrate, F-I-L-T-R-A-T-E. And when the renal filtrate is leaving the nephron, then it will become urine. So as long as it stays in the nephron, it is not urine, it is the renal filtrate. And that renal filtrate is actually your blood plasma derived from blood plasma. So your blood plasma, our blood plasma, is being cleansed by the nephron, right? So when we say whole blood, there are 2 parts of it, the blood plasma and the formed elements. The formed elements are not supposed to leave the capillary bed. The formed elements, the white blood cells, the white blood cells, the platelets, and the plasma proteins, they're too big, and you want them to be big. They are not supposed to be filtered. They're not supposed to leave the capillary bed. Only anything that is dissolved in your blood plasma, the water-based part of the blood, can leave the capillary bed, right? By size. So anything that's smaller than the pore, the filter of the glomerulus, the capillary bed, will allow to leave the blood plasma and become the renal filtrate. If you are an entity that size-wise, you are bigger than the pore of the glomerular membrane, you will remain within the glomerulus. You will not be cleansed out, okay? So we're gonna get back to that later. It's very, very mesmerizing. It's a very interesting concept. How the body is basically, how the glomerulus is actually cleansing, filtering, if you will, our blood. Okay, so that's basically a quick review about the anatomy of a nephron, and going into detail here about the glomerulus. So again, one more time, you have the Bowman's capsule and you have the capillary bed glomerulus, and you have, this is part of the PCT, proximal convoluted tubule, and inside here, all that space, it contains a renal filtrate. All that blue part, all of that coming out here, that's a renal filtrate, RF, okay? In here is blood containing blood plasma, BP stands for blood plasma, that can be filtered out by this glomerulus. So this is the capillary bed, glomerulus. You have the arriving blood vessel, you're having the exiting blood vessel. So blood goes in to be cleansed and blood coming back out, leaving the glomerulus. And what remains in here is the renal filtrate. So that filtrate was actually the filtered blood plasma. And you have 1 million of these nephron with its associated glomerulus per kidney, okay? I mentioned this earlier. So high resistant capillary beds are fed and drained by arterioles, the arriving and the exiting arterioles. Okay, so this is unique to a glomerulus. Nowhere else in the human body you will find this arrangement. Okay, a capillary bed flanked by both artery types. The entry and the exit of that capillary bed is being flanked, served by both artery type blood vessels. Over here, the renal tubule I mentioned earlier. So it's a glomerular capsule, also known as Bowman's capsule. So the glomerular capsule is upstream. So this is how it goes. So you start with glomerular capsule. You're gonna go into the PCT. So I'm talking about the renal filtrate, okay? So the renal filtrate is leaving the glomerular capsule. It goes into the PCT. From the PCT, it's gonna flow into the loop of Henle. And from the loop of Henle, it will flow into the DCT. And the DCT will be connected to the collecting duct. Okay. Now, what is amazing also, and this you should, learn that from anatomy. Each nephron is connected to the collecting duct by a special tubule here. And that part is called a connecting tubule. Okay, connecting tubule. So each nephron has its own exclusive connecting tubule. And this connecting tubule is connecting that nephron to the collecting duct, okay, down here. Collecting and connecting, okay? Collecting, C-O-L-L-E-C-T-I-N-G, whereas connecting is C-O-N-N-E-C-T-I-N-G. So the connecting duct is this, is over here. This part here is shown here. Okay. And as soon as that renal filtrate gets to the collecting duct, in here and in here, we are talking about urine. It's no more renal filtrate. Okay. So the collecting duct is just a larger tube that basically receives urinary sample, urine, a volume urine, and then it will be transported to and stored in the urinary bladder. And again, cortical nephron versus juxtamedullary nephron. 85% of all the nephrons are cortical nephrons. 15% of all nephrons are called juxtamedullary nephrons. They are also located differently to most of the entire cortical nephron, most of it structure-wise, yet almost the entire structure is located in the cortex, the renal cortex, the superficial layer in the kidney. The juxtamedullary nephron is actually located at the boundary between the renal cortex and the renal medulla. So that's the first difference between the two in terms of anatomical location. In terms of structure, we talk about this, the cortical nephrons have shorter loop of Henle. You have actually shown here, this is the shorter loop Henle. The juxtamedullary nephron has a larger, longer loop of Henle, and some of them actually have the same length as the entire height of the medulla, the renal medulla, the deeper region within the kidney. So this loop is extremely long. And not only that, each loop of Henle have their own unique capillary bed that interacts with the loop. I'm gonna do different colors here. So the blue one is the peritubular capillary. The red one is a vasa recta. Okay. And the cortical nephrons, they produce dilute urine. The juxtamedullary, they produce concentrated urine. So we're connecting anatomy to physio. So whatever you learn from anatomy, we take it to another level here. Moving on to the next one. There's a region in the nephron, and this is an important region. It's called the juxtaglomerular apparatus. There are actually 3 different types of cells that are highly involved in allowing the nephron to regulate blood flow, blood perfusion. This is an extremely important concept. The arriving arteriole here allows blood to go inside each glomerulus. Now, blood pressure in the systemic circulation fluctuates a lot. Simply by when you're lying on bed and then you just jump on your feet, instantaneously blood pressure changes, and you don't take that for granted, right? Because you're young now. But the body, that's basically, it needs to maintain homeostasis. So it's almost instantaneously, it readjusts. But that fluctuation in blood pressure, if you apply that into the glomerular capillaries, you're going to destroy them instantaneously too. So that blood pressure fluctuation in the systemic vascular bed is not translated into the local glomerular blood pressure. It's being basically maintained. That fluctuation, we're going to get to that later in the lecture as to how this is possible. But the cells here are basically allowing that to happen. So one of the cells is called macula densa. This is they are simple columnar epithelial cells. So they look like column shaped, and they are in the wall of the ascending limb of the Henle's loop, or depending on the medical textbook, because it's a gray zone, there's no defined boundary. It's either in the ascending limb of the Henle's loop of Henle, or the distal convoluted tubule. It doesn't matter where the boundary is. What matters is this type of cells is distinctly unique in terms of shape and in terms of what they do. The macula densa cells are actually, they are sensitive to the concentration of certain chemicals in the renal filtrate. Most notably, sodium, right? So they're extremely sensitive to the concentration of sodium in the renal filtrate. So if they detect a high concentration of sodium in the renal filtrate, they will send a paracrine signal, a paracrine chemical messenger. Remember paracrine? Paracrine means short distance communication chemical messenger, right? This paracrine or paracrine signal will go and allow the afferent arteriole here, the arriving blood vessel, to constrict, to slow down blood perfusion into the glomerulus. And here's why. If you have sodium in the renal filtrate and that sodium concentration is high, it means one thing. Blood perfusion in the glomerulus was too high. So it's a negative feedback mechanism. So when the concentration of sodium in the renal filtrate is high, as far as the nephron is concerned, it equates that with high blood perfusion in the glomerulus. And it will respond to that by decreasing it. So it will send a chemical messenger. At this point, we don't know the identity of that chemical messenger. So you can use that as a PhD thesis, if you will, to get your PhD degree. So that paracrine or paracrine signal, that chemical messenger, will go to the afferent arteriole and will induce its constriction. So when it's constrict, it will slow down blood flow into each glomerulus, thereby decreasing again that sodium concentration. Okay. So this is one way where the macula densa dictates, have a say regulating blood perfusion, blood pressure going into each glomerulus. Another one is in the wall of the afferent arteriole itself. They are called granular cells. These are detecting blood pressure. These are sensitive to the stretch in the wall of these afferent arterioles. So they are called mechanoreceptors. They are sensitive to the pressure in the blood that comes into each glomerulus. So if that blood pressure is high, it will expand the afferent arteriole. And when the afferent arteriole expands, the juxtaglomerular or granular cells constrict, decreasing blood flow into each glomerulus. So that's a second mechanism controlling blood pressure going into the glomerulus to protect that glomerulus. Because your glomeruli cannot sustain blood pressure, excessive blood pressure continuously, because they will be destroyed. Remember I talked about the wall? This glomerulus is a capillary bed. And capillary bed, we learn from anatomy, they have thin walls because they are meant for gas exchange and nutrient and waste exchange. So the thin walls are basically allowing efficient exchange. But because of that, they are also fragile. They are basically very, very sensitive to high blood pressure, and they can burst. So because of this, these two macular densa cells and the granular cells are there to protect against wild blood fluctuation in this localized vascular bed, specifically the glomerulus. There's a third type of cells. They are called mesangial cells, and they are basically also have these phagocytic properties. They protect the kidneys so they can neutralize undesired material through phagocytosis, but they can also constrict. So they are located in the each capillary, and they're acting like a sphincter. So the pre-capillary sphincter, they can contract, they can constrict, thereby slowing down blood perfusion in the glomerulus, right? So this here, this slide, this is slide number 5. You keep track of this because we will talk about this concept again when we hit slide number 9. Okay, so keep that in back burner. We're going to come back to slide number 5, this concept, because it is part of the kidney's ability to control blood pressure locally. Especially these mesangial cells, they are part of what is called the intrinsic mechanism. Okay, controlling blood flow, perfusing each glomerulus. Next item, the filtration membrane. This is the glomerular filtration membrane. We have on one side of the membrane, we have this part here. This is a capillary bed, so this is inside the glomerulus. So plasma in lumen of capillary. So plasma here, we're talking about blood plasma, to be correct. BP, and the capillary, we are talking about the glomerulus, to be correct. Okay. So the capillary endothelial cells, these are simple squamous epithelium or simple squamous epithelial cells. Okay. So they are disc-shaped, very flat cells. They are used when you want the body needs to build a thin membrane. The basement membrane is basically produced by the connective tissue. And this basement membrane is a non-cellular components. So it has, for example, extracellular proteins that are anchoring on both sides of the membrane here, the cells. On the other side, the tubule side, we have epithelial cells that are called podocyte. These cells have a unique feature of extending, the plasma membrane and the wrap around the entire basement membrane. So let me see if I can show you. So these are the podocyte right here. So that's, you see clearly the nucleus of that podocyte, and it sends out extensions. So it covers, it surrounds the glomerulus, the capillary bed here, right? So going back. And then there are pores, and the pores are called fenestrations. So this here, the fenestration is an opening, a pore, P-O-R-E, right? The mechanism of transport here, we've seen this already. And it's driven by passive transport mechanism, meaning the pressure will drive the transfer of chemical solutes from the capillary bed into the space here, Bowman capsule space. And it's based on size. So everything will be pushed in here and go through here. And that is driven by a pressure gradient, delta P. Okay, we are not talking about concentration gradient. We are talking about pressure gradient. So it goes from high pressure to low pressure. And the only limitation, in addition to the pressure gradient, is size of the solute. So if any entity that is smaller than the pore, smaller than the fenestration, will be pushed from the blood plasma into the renal filtrate side. Okay? And at this step here, we call that glomerular filtration. Okay, it's a passive transport mechanism, meaning it does not require cellular energy. It does not require ATP. It is simply driven by a pressure gradient. It goes from high pressure to low pressure. And it goes through this pore here, this opening, and that's dictated by size. So if you are smaller than the pore, you will be pushed through. If you are larger than the pore, you stay behind. You remain in the capillary. You remain in the glomerulus, right? So this glomerular filtration will basically filter anything that is smaller than the pore. And that, unfortunately, glucose will be filtered out. Amino acids will be filtered out. So those are the two most important desired nutrients. It will be filtered out because they're smaller than the pore. So you actually, at this point, you're actually losing nutrients too. So in the process of cleansing that blood plasma, you are also ridding yourself of desired material, desired nutrients, in this case, glucose and amino acids. But they will be reclaimed later in the nephron, okay? But at this point, since it's passive transport, there's no selectivity here. The only selectivity, if you will, is the size of the nutrients. So plasma proteins are too big, they remain in the blood vessel, remain in the glomerulus. Red blood cells, white blood cells, platelets are too big, they remain in the glomerulus. Proteins such as hormones, enzymes, they remain in the glomerulus. They cannot be filtered. Some of the albumins, since they're so small in size, you should have traces of albumin in the urine, but not much, even under healthy conditions. Under renal failure, this is the problem when that filtration membrane, the glomerular filtration membrane, is compromised. the pores are so large that plasma proteins now can go through, then we have a problem. Okay, but not under healthy conditions. Under healthy conditions, you're not supposed to see significant amount of plasma proteins in your patient's urine samples. Okay. Oops. So basically, that's what I said, most of it here. So you can go ahead and reread that on your own. There's nothing cerebral there. So I'm not going to go back and repeat myself. I'm going to go on to the next one to explain abstract concepts. So glomerular filtration. Urine production is being performed by three steps, by three mechanisms. The first one is glomerular filtration, or simply filtration. So when we talk about urine, it's basically urine excretion here. E equals filtration plus secretion minus reabsorption. Yeah. So what F here, we are talking about this one, glomerular filtration. And that F, the first step in the process, is passive transport. Passive transport specifically is driven by pressure gradient, high pressure to low pressure. Okay. When we talk about filtration, I'm exactly on page 512, 512 of your Stanfield textbook. And it's on top of the page, on the right side of the page, it's underneath glomerular filtration rate. It shows you factors, right? So there are actually 4 factors involved here that have a say in producing that filtration. I'm showing you only 3 factors here. I'm going to get to it as to why. The 4th factor, one of the factors is it's not significant. So let me begin with the first one here. So there are pressure promoting filtration, and there are pressures promoting reabsorption, meaning you look at the opposite arrows. So the black arrows are basically for filtration, and the pale purple arrow and the blue arrow is for reabsorption, meaning the renal filtrate, it goes back into the blood vessel, whereas filtration is blood plasma leaving and becoming renal filtrate. Okay. So the main pressure, called the glomerular blood pressure, GBHP here, glomerular blood hydrostatic pressure. This is due to your blood pressure inside your glomerulus at around 55 millimercury. Okay, so that's the force, the pressure that pushes blood plasma, induces blood plasma to leave the glomerulus and go into the Bowman's capsular space, the space in the Bowman's capsule. There's also traces of plasma protein in the Bowman's capsule that also attracts blood plasma out into that space. But that component is negligible under healthy conditions. That's why it's being ignored. So in your book, it shows you, in your book, instead of 55 millimercury, it says 60 millimercury. So it doesn't really matter the exact number. What matters is the concept, right? So either 55 or 60, that's the blood pressure that promotes filtration, promotes blood plasma to leave the glomerulus and going into the glomerular or Bowman's capsular space. The 0 millimercury in your book, that's exactly it. This is due to the, how do I say this? The solute in the capsular space that has the ability to attract water from the glomerulus into that capsular space. But under healthy conditions, it's not significant. It's not enough force to that, so we ignore that. So it's equal to 0. So the two component that promotes filtration is the blood pressure in the glomerulus and the water pressure in the Bowman's capsule, which is 0 millimercury, because it's negligible. It becomes significant only under pathological conditions. For example, patient suffering renal failure, and this component here becomes significant, because then you have proteins leaking out from the glomerulus into the Bowman's capsular space, then this becomes a significant number. But under healthy conditions, it's around 0, it's negligible. So those are the two pressure promoting filtration. The next two are opposing filtration, meaning they are basically promoting the filtrate to go back into the glomerulus. So the water pressure in the Bowman's capsule at 15 millimercury, and also the blood colloid osmotic pressure here, so promoting, this is due to the plasma protein, the proteins inside the blood vessel, the glomerulus, attracting water back in, right? So BCOP stands for blood colloid osmotic pressure, and this is due to proteins inside the glomerulus attracting water back in at 30 millimercury. So if you have 55 on one side and 45 on the other, you have a net filtration of about 10 millimercury. That seems small, but that's enough to promote filtration. So the net filtration is 10 millimercury. In your book, it says 16. Again, the number is not important. The concept is, okay? So net filtration pressure is the blood pressure that promotes glomerular filtration. And it's around 10 millimercury. Okay? So this is how blood plasma is being filtered passively at the glomerular, across the glomerular membrane. And so the first step of urine production is glomerular filtration. And this is exclusively a passive transport mechanism, meaning there's absolutely no selectivity aside from the fact of the pore size. That's the only thing. So there's no selectivity at all. If you're smaller than the pore, you go through. If you're larger than the pore, you stay behind. You remain in the vascular bed. If you're small enough, you will be in the tubules, starting with the Bowman's capsular space and then ultimately leaving it and going to the PCT, loop of Henle, DCT, ultimately the collecting duct and becoming urine. Now we can, we're gonna talk later, but for now, we know the glomerular filtration rate in healthy males and females. So it is expressed as the volume per unit time. In this case here, it's around 125 ml, 125 cc's per minute in males, and slightly more than 100 cc's per minute in female, and that's for both kidneys. So in other words, every minute, your blood plasma, 125 cc's, anywhere from 100 to 125 cc's of blood plasma are being filtered by the human kidneys per minute. Okay, and we're going to talk about that later, but keep that in the back burner. The reason is this: the blood that comes into the glomerulus, it's around 625 cc's or ml per minute. This is called a renal plasma flow. Renal plasma flow. The amount of blood plasma going into the glomerulus. And of that 625 ml, only 125 ml are being filtered. This is an important concept, guys. In other words, the anatomy of the nephron, the relationship between the nephron and each glomerulus will not allow blood plasma to be cleansed at 100%. So it's only a fraction of what comes in that will be filtered. So that fraction is around 20%. Right? So 80% of the incoming blood plasma remains as is, has not been cleansed, has not been filtered of cellular waste, of debris, whatever you call it, that needs to be filtered. It remains inside your vascular bed. So in other words, it requires multiple trips to the kidneys to cleanse your blood. It takes time, right? Because every time the volume of blood that comes into each glomerulus, only 1/5 of it, only 20% of it will be cleared, will be cleansed, will be filtered out. 4/5 of it, 80% of it remains in your vascular bed. So every time you can only cleanse 20% of it. So it requires multiple trips to the waste management center to really clear a toxic substance, undesired material like cellular waste. And that's an important concept. And we call that filtration fraction. It's only 20%. So make sure that you understand this. Now here's the slide 9 that I talk about the relationship between the 5th slide and the 9th slide, slide number 5 and slide number 9. If you look closely over here, this is the fluctuation in your systemic blood pressure, SBP, okay? So it can fluctuate a lot. So mean arterial pressure, this is we learned that from the previous unit. I hope you remember this. MAP, M-A-P. MAP draws blood from point A to point B within your systemic vascular bed. Okay, I did say systemic, right? So systemic versus local vascular bed, meaning systemic means freeway 5, freeway 99. Local vascular beds means when you exit, get into Stockton, okay? So as you go out into the exits along the, or multiple exits, when you go into Stockton area, so each exit will basically lead you into smaller roads. So that's your localized, local circulation, local circuits, local blood perfusion. So on the freeway, the speed is always high. It can fluctuate, but once you take that exit, the flow, the speed of the cars are more controlled. It's the same thing here. So even though the systemic vascular bed fluctuates a lot, I want you to draw your attention about this flat line here. This is amazing. When your systemic vascular bed fluctuate over 100 millimercury, your glomerular filtration rate remains the same at 125. This is fluctuating between 80, changing between 80 and 180 in the systemic vascular bed, yet in the glomerular bed, it's only 125. It is maintained. Okay, the blood pressure remains the same so that you can have the same glomerular filtration rate. If the glomerular filtration rate is not the same, it means blood pressure inside the glomerulus is not contained, it's not regulated. And that over long term, the glomerular filtration membrane will be destroyed. And this is an important concept. So there are three ways, three mechanisms available to maintain this glomerular filtration rate constant over a wide range of MAP fluctuation in our systemic vascular bed, systemic blood pressure, okay? So what are these three mechanisms that allows the body to maintain that stable GFR, glomerular filtration rate, despite the fluctuation in the mean arterial pressure in a systemic vascular bed? The three mechanisms are listed here. The first one, the renal autoregulation. These are intrinsic mechanism. They belong to the kidneys. So intrinsic. INTRINSIC. And under intrinsic, there are three ways where the kidneys can control to maintain that constant GFR. The first one is the myogenic mechanism. This is the same that we learned in the previous unit. So in the wall of that afferent arterioles, those afferent arterioles are smooth muscles. When blood pressure increases, when blood flows into the afferent arteriole has high pressure, it will expand the wall of these afferent arterioles. And when the smooth muscle cells in the wall of these afferent arterioles are extended, or expand, are stretched out, they respond by constricting it, they're contracting. So as blood pressure increases, the afferent arterioles constrict to decrease the pressure, decreasing blood flow. So to allow maintaining the same rate of glomerular filtration. That's one mechanism. The second mechanism is the tubuloglomerular feedback through macular denser we talked earlier on slide number 5. So they detect, they're sensitive to the concentration of electrolytes, mostly sodium in the renal, sodium concentration in the renal filtrate, and they send a chemical signals to the afferent arteriole, inducing them to constrict so that to slow down incoming blood into the glomerulus, so to maintain that filtration rate. And the third one is those the same mesangial cells that I mentioned. They act like a precapillary sphincter. They constrict, therefore decreasing blood flow through the glomerulus. So you can have, so that it allows the kidneys to maintain a constant GFR. So all three mechanisms belong to the kidney. That's what we call it renal auto-regulation. These are intrinsic mechanisms. They're not involving any other organ systems. The second one involves the central nervous system or the nervous system, neuroregulation. So sympathetic nerve fibers, these are sympathetic ganglionic neurons sending their axons, so we call them sympathetic nerve fibers, and they make a neurojunctional, neuroeffector junctions with the kidneys, and then they release neurotransmitters called norepinephrine. And in this case here, the norepinephrine will basically induce the constriction of the smooth muscle in the afferent arterioles. And this is, by the way, this is the same signaling cascade that you learned from the previous unit. So NE is basically binding to beta adrenergic receptors, kickstarting the signaling cascade that we learned from the previous unit, and leading to the responses, in this case, smooth muscle in the walls of the afferent arterioles will constrict, slowing blood flow into the glomerulus. Okay. And then the third mechanism is hormones. So the endocrine system releasing renin, and this is one of the most beautiful, most powerful signaling cascade, leading to the production of the most, if not one of the most powerful vasoconstrictor. And let me go a little bit slower here. So what you have is the following. You have a protein. It's called angiotensinogen. So ANGIOTENSINOGEN. This angiotensinogen is a glycoprotein. Glycoprotein means a protein with sugar groups attached to it. It is produced by the liver, and it belongs to plasma protein. This is an example of plasma protein. We have three families of plasma proteins, right? From anatomy, we have the albumins, we have the globulins, and we have the fibrinogens. The angiotensinogen here belongs to the second family, the globulins. And it is produced by the liver and then it's released into the bloodstream, right? So it's floating in the bloodstream. These plasma proteins, a glycoprotein called angiotensinogen. And when the sympathetic division induces the kidney to release renin, renin will basically cleave the angiotensinogen, will cut. Renin acts like a protease. It will cut the angiotensinogen into a smaller protein called angiotensin 1. Roman numeral 1, okay? Angiotensin 1. And that angiotensin 1 will be converted by another enzyme, shortened ACE, A-C-E. A stands for angiotensin converting enzyme. And ACE converts angiotensin 1 into angiotensin 2. So I'm going to simply write A2 here, okay? A here stands for the same word, angiotensin. So angiotensin 2. And it is this angiotensin 2 that is one of the more remarkable chemical. This is one of the most strongest vasoconstrictor. It will induce the smooth muscle in the wall of your blood vessels to constrict, vasoconstrictor. So it will slow down the glomerular filtration rate. And that's not the end of the story. The angiotensin 2 here will induce the kidney also to release the adrenal cortex, aldosterone. This is a D. Okay. ALDOSTERONE. This aldosterone is produced by our adrenal cortex. This is a steroid hormone. It's a mineralocorticoid. And what it does, it will basically involve, it allows the kidney to basically, it maintain homeostasis of sodium and potassium, but most importantly, sodium homeostasis. So in other words, it helps the body to retain sodium. And remember, wherever salt goes, water follows. It will also induce the body to retain water. Okay, so that's the consequence of releasing angiotensin 2. So it will indirectly induce the release of aldosterone, and aldosterone is involved in maintaining electrolyte homeostasis, notably sodium and potassium. And that effect is on the kidney. So we're going to come back to the next recording and revisit this concept, the capability of this steroid hormones, aldosterone, in involving in the maintaining electrolyte homeostasis, mostly sodium, and to some less extent potassium cations. Okay. This one here, this table, there's nothing cerebral about this. It's just to show you most of these chemicals are, even though they're filtered, but they will be reclaimed by tubular reabsorption. And I stress the word here, it's not absorption, it's reabsorption. Right? Because these chemicals were filtered out, right? Well, they were pushed out from the glomerulus, the vascular side, into the tubular side. And unfortunately, we need water, we need glucose, we need all these electrolytes, sodium, potassium, calcium, chloride, bicarbonate, right? Amino acid, even though on this list is not shown, add to that amino acids, They are excruciating, very critical. So they are the building blocks of proteins, right? So they are part of our nutrients. So glucose and amino acids were filtered out completely, but they need to be reclaimed. And in fact, they are being reclaimed at the proximal convoluted tubule, right? So that's the main job of the PCT, is to reclaim the desired chemicals, our nutrients, our water, our electrolytes. 60% of the water is reclaimed. 60% of the filtered water at the glomeruli, across the glomerular membrane, will be reclaimed by the PCT. Most of the sodium will be reclaimed by the PCT as well, right? So, including bicarbonate. Bicarbonate is an extremely important chemical that we get to know in more detail on the next recording about its importance, not only as a buffer, but we'll get to talk about that later, okay? Including urea. Even though urea is a cellular waste product, the kidneys retain urea up to 60%, right? Urea is being kept in our kidneys because that cellular waste is helping the kidney to concentrate urine, right? So we only dispose 40% of our urea as waste. The other 60% is retained in the kidney, in the interstitial space of the kidney, in the medullary region of the kidney, and it is actively being utilized, helping the kidney, helping the juxtamedullary nephrons to concentrate the urine under conditions where we are completely dehydrated. Now, how are glucose molecule being reabsorbed at the proximal convoluted tubule? And surprisingly, we learned about this mechanism, right? Glucose is being reabsorbed across two boundaries. The first boundary is at the apical membrane. And the second boundary is at the basolateral membrane. Okay? Apical membranes mean the surface here. So what you have here, this is important. This compartment, this is your renal filtrate. Okay? This area here, all of this is your PCT, proximal convoluted tubule. So this is the luminal side of the proximal convoluted tubule. Luminal, L-U-M-I-N-A-L. So the luminal side of the PCT contains a renal filtrate. And that renal filtrate contains glucose because glucose was filtered out, right? So at the apical membrane, glucose transport is through secondary active transport. Again, I'm going to say it again. At the apical membrane, glucose gets inside the tubular cells. So this cell here is simple cuboidal epithelial cell. The cell looks like a cube, right? Simple cuboidal epithelial cell. So glucose gets from the luminal side of the proximal convoluted tubule, meaning glucose from the renal filtrate, gets into the simple cuboidal epithelial cell lining the wall of the PCT by secondary active transport. It's the same mechanism we learned earlier. This is through a symporter, right? A transmembrane protein that transport two different cargoes at the same time in the same direction. So this transporter transports sodium and then glucose tag along. It's a free ride. Now, in order for this sodium to get in, that sodium concentration gradient needs to be established. And that establishment is by the sodium potassium ATPase that is located at the basal lateral membrane. So this sodium potassium ATPase consume energy, ATP, to create that sodium concentration gradient. So it's extruding, kicking sodium out. So on the intracellular side of the simple cuboidal epithelial cell, you have less sodium than on the luminal side here, on the renal filtrate side. So sodium will go from high concentration into lower concentration through that symporter. So when the symporter drives sodium from high concentration on the renal filtrate side into the intracellular side of a simple cuboidal cell, glucose just tag along. So once glucose gets inside the simple cuboidal epithelial cell lining the wall of the PCT, it's simply being transported out and gets into this here. This is a capillary bed that we call this peritubular capillary. Assuming this is the cortical nephron, the nephron that is responsible to produce dilute urine. Okay? Now this is through passive transport. This is an example of a facilitated diffusion. It's a passive transport mechanism. So there are glucose transporter transporting glucose from the intracellular, the cytoplasm of the simple cuboidal epithelial cells, moving glucose out into the peritubular capillary. So this transport mechanism does not require cellular energy, does not require ATP. It is driven by the concentration of glucose. That gradient is being higher from the cytoplasm of the simple cuboidal epithelial cell than on the outside interstitial space here. So that's why glucose gets out and simply diffuses across this endothelial cell here, the thin membrane of that capillary we call peritubular capillary. So this is how glucose is reclaimed by the PCT, okay, being reabsorbed by the PCT, more specifically by the simple cuboidal epithelial cells that are lining in the wall of the proximal convoluted tubule. Isn't that beautiful, guys? It's gorgeous. Right? We just apply what we learned from the beginning of the semester. So everything that you learn about transport comes back. So you haven't wasted anything yet. So that you know. Now moving on to a very beautiful concept, the concept of clearance. Clearance means the ability of the kidneys, in this case specifically nephrons, to cleanse your blood plasma, to clear, to take away a solute, to take away a chemical from our blood plasma. Now, this clearing concept relies on how the kidneys produce urine. So E here stands for excretion. So this is how the kidney gets rid of a solute, a waste, a chemical, excretion, EX, CRETION. F stands for filtration, more specifically glomerular filtration. S for secretion. R for reabsorption, right? So F is done by the glomerulus. Secretion is done by distal convoluted tubule. Reabsorption is done by proximal convoluted tubule. Now, why is it that there's a plus sign here and a minus sign here? The reason is very simple. Both filtration and secretion goes in the same direction, right? Meaning the solute will leave the vascular bed and gets into the tubular space, right? So filtration, it gets into the Bowman capsules, capsular space, and secretion here, the DCT will get into the distal convoluted tubule. So both of them promote, they're leaving the body. Whereas reabsorption is the opposite direction. That's why you have to subtract that out. So this is moving from the tubular space back into the vascular bed. So this is where you reabsorb your water, you reabsorb your nutrients, you reabsorb your electrolytes, right? So all of that is performed by the proximal convoluted tubule. So that's the basic definition. Now, let's say using this concept in a clinical setting, if you think about it, if we have a chemical that is filtered, right, by the glomeruli, but that chemical is not being secreted and cannot be reabsorbed, what do you have is you can use that chemical and you can estimate the GFR because that excretion rate is the same as the filtration rate. So let me repeat. If there's a chemical that the body only filters it, the kidneys, the nephrons, only filters that chemical, but the nephron is not secreting that same chemical, and the nephron is not reabsorbing that same chemical. Of the three mechanisms, it only filters it. So if you have that chemical and you give it to your patient, you can, and that the amount of the chemical that's in your urine, the patient's urine, you can go back, and because that amount, that concentration reflects the rate at which the filtration of the glomeruli is happening. Okay, so we do have that chemical, and that chemical is called inulin. So when you give the patients inulin, you can estimate GFR. This is how we arrive at the GFR at 125 cc's for male and 105 cc for females in terms of GFR, male, female, that we saw earlier in the lecture for GFR, glomerular filtration rate. Unfortunately, we cannot take inulin by mouth, right? It's per os. We cannot do that. We have to infuse, so this is a pretty invasive procedure. So it's not ideal. It needs to be done in clinical setting and under supervision. You just can't give inulin to the patient by mouth. So he or she needs to come in. We need to infuse inulin into the body, and so that we can estimate GFR. Now, there's a compromise to this. There's another chemical that it's not you don't need to give it to your patient. It's produced by the body, and this chemical is a waste product called creatinine. Oops. Okay. creatinine. This creatinine is a waste product from protein catabolism. So as your cell breaks down protein, generates a waste, and this waste is called creatinine. And the body does secrete, that does filter creatinine, most of it. It is also slightly, ever slightly, secreting creatinine. It's not being reabsorbed, right? So when we get the value here for E, it's around 140. So we know that it's not perfectly the true value of GFR. It gives us a ballpark estimate. The reason why we do this is quick and dirty is because we don't need to give the patient anything. Okay, it's already produced by the body. So it doesn't give as an accurate estimate compared to inulin, but it doesn't implicate an invasive procedure in the case of inulin to get a GFR. So when we measure the rate of excretion of creatinine, we also know the status of the GFR in our patient. Okay. Moving on to the next slide, because it's the same, using another chemical to apply to another concept. And this is the PAL clearance coming into play. Um, let's go back here. There's another concept where, think about when you have a chemical that is filtered, both filtered and secreted, but is not being reabsorbed. Okay. So whatever you give the patient, it ends up in the urine, but the body fails to reabsorb it. And we do have such a chemical. Let's go on the next slide. Let me erase this first. Okay. So this chemical PAH, para-amino hippuric acid. Let me go over here. So this PAH is filtered, is being secreted by the distal convoluted tubule, but it's not being reabsorbed by the proximal convoluted tubule. Okay, again, PAH being filtered by the glomeruli, being secreted actively by the distal convoluted tubule, but is not being reabsorbed by the proximal convoluted tubule. Okay? And whatever you have, give it to the patient will basically end up excreting it. So if you're using this chemical, PHA, the excretion of PHA will allow you to give you an estimate of your renal blood plasma flow. In other words, the blood plasma, the volume, the amount of blood plasma flowing through your glomeruli. And why is that important? Because if you know the renal plasma flow, then you will know the renal blood flow. Okay, the reason is when you talk about whole blood, you have 45% of that whole blood is your red blood cells. Less than 1% of it, so we ignore that. The white blood cells and platelets is less than 1%, so we ignore that. And then the remaining 55% is your blood plasma, the water-based blood plasma. Okay? Now, if you have a renal plasma flow at 625 ml cc's per minute, the percentage of red blood cell in your whole blood is called hematocrit. This word here, HEMATOCRIT. So the hematocrit is around 45%. So you subtract that 45 from 55, so you end up doing 625 ml divided by 0.55. Okay. How did I get the 0.55? It's just 1 minus 0.45. And if you do this fraction ratio, you will get this value. This is the renal blood flow. The amount of blood flowing to your kidneys per minute. And this, why is it important? It is important because it's around 25% of the cardiac output. So assuming that it's around, around a quarter, 25% of the cardiac output goes to the kidneys, right? So every time that your body wants to cleanse your blood, it takes time because only 25% of the cardiac output, the total volume of blood coming out of the heart, only a quarter of it will go to the kidney. And of that is only 1/5 of it is being cleansed. So it takes multiple trips in order for the kidneys to cleanse undesired material, cellular waste, medications, you name it, right? So it's not possible for anything in your vascular bed to be cleansed right away. This is completely statistical, completely random. So one single molecule of a waste can remain in your body by chance over a long period of time because simply the fact that one cardiac output, it fails to go to either kidney because only a quarter of that blood output goes to the kidneys, meaning 75% remaining is not going to the kidney, right? Imagine on the freeway, you have 100 cars, okay? 100 cars, 99 of them are red. One is black. The black is the cellular waste. Just assuming that. And every time you go through Stockton, choose an exit, right? So every time there's an exit, there's only 25 cars that can get out. So the 75 car that remains keeps on going. They have to wait onto the next trip coming back, because the cardiovascular system is circular. It's a circuit, comes back, and it repeats the process. So by chance, that black car will never take the exit. It remains in the systemic circulation for a long period of time. So that's what I'm trying to say here. So because of that extraction being only a quarter of the cardiac output, and when you get into the glomeruli, only a fifth of it is actually being filtered, we have a problem. So that's why it takes time to clear medication. So when you get to nursing school or in the clinical setting, there's another concept when you take pharmacology class. It's called a half-life of a medication. And that half-life is important. In other words, let's say the half-life concept is, let's say it has a half-life of 3 hours, meaning every 3 hours, your body is capable of clearing it by half, right? So let's say you started with a dose of 1 milligram, and the half-life is 5 hours, right? So you give the patient 1 milligram of that medication. 5 hours later, in your patient's system, it remains half a milligram. Add another 5 hours, so 10 hours after ingestion of the medication, the patient remains a quarter of a milligram. And you go on like, so every half-life, it basically drops by half, okay? So it's another concept. And not only that, it depends on also water solubility of that medication. So if the medication is fat soluble, oh, God help you, because it's going to take more time to clear that drug. Because if it's fat soluble, it will basically be hiding in your cells, because they can cross membranes. So it takes a longer time to clear that fat soluble medication, which leads me to bring up another issue. It's called volume of distribution, right? So if the medication is fat soluble, it has a very large volume distribution because it can get to everywhere. But if the medication is water soluble, it's much more restrained, much more contained. It's easier for your system to clear it. So the concept of clearance will come back in pharmacology in nursing school. The concept of volume distribution will come back in nursing school. But when you get to that, remember me, okay? Okay, so on that note, I'm gonna end today's recording, and then I will see you next time.